Okay, so I thought I would make this update video on the compressible friction force. In a previous video, I showed an equation for it, which I uh, now know is not um, correct, I believe. Um, this time is going to be the actual um, generalized compressible friction force, and if you plug this in for the friction force in the Navier-Stokes equation, it would be the true solution for how a fluid flows in real life. Um, um, you know, water, for example, will use the original the simplified one that we use, which is viscosity times the Laplacian of u. That will work for water. But this one is actually needed if you really want to understand how it happens with air in the atmosphere. But I should note that, a lot of these terms, um, if you assume that this mu viscosity is constant, you can pull it out, and you end up getting the same thing plus this extra term. Um, and if they are not constant, then you're going to be pretty much stuck with this form. Um, and then we'll find later, this will go away if we have an incompressible fluid like water, which gets us to um, this form here. Anyways, the full form is I'll just go over it real quick. So it's actually um, when we were deriving the um, the viscous force or friction force, we used a stress tensor. Um, But in that case, we didn't really show, I didn't really show the whole stress tensor, but this is really a bunch of tensors. So we've been working with things like, uh, the div operator, divergence, or sorry, del operator, divergence, or gradient, which are vector operations. These are vectors of vectors. So there's actually vectors inside the vectors. So what we have is, and when we take this whole thing is going to be called tau, the stress tensor. When you take the divergence of a stress tensor, you actually get a vector, just like this would also be a vector. And so what we have here is we have alpha, which is the uh, 1 over the density times the divergence of the stress tensor, which has the viscosity mu times the gradient of u of the velocity, the 3D velocity vector, plus the transpose of the gradient of the 3D velocity vector. So it's like this. And minus 2/3 times mu, the viscosity, times the divergence of the velocity vector times the identity tensor. The identity tensor is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. And this identity tensor is because the fluid is isotropic, which means it's supposed to work. The way this friction works is actually the same in all directions. And finally, we have the gradient of the I believe this is the bulk viscosity um, times the divergence of the fluid. And so this equation, being compressible, explains how the fluid compresses and expands, and also how the fluid deforms under rotational stress, which is, of course, happens in the air, um, in the atmosphere, for example. So just first, we're going to look at this term, um, the gradient of the divergence term. You can just write out the gradient, which is this, then you write out the bulk viscosity, and then you write out the divergence, and then you just do some multiplication, you'll end up with this. Um, so yeah, so this would be for the x direction, y direction, and then z direction. And then when you talk about these tensors here, you can write it in this form where you have six components. Like this would be the I direction in the I direction. This would be J in the J direction and K in the K direction, the K direction. And for example, if we go here, this will be um, like an I direction in the K direction kind of situation. So this is a tensor, and you can write it as a matrix of um, derivatives. And then since it's the matrix, we now know, okay, the transpose, you simply take this row and convert it into a column, same here and same here. And then for this term in here, it's just going to look like this. It's going to be divergence on the diagonals and zero everywhere else. And if you add up all of these terms, which we remember we called as tau, the stress tensor, you'll get something that looks like this. We'll just call it tau or T or whatever. We call it tau because it's referring to the stress, um, which is a physical property. And this is just a notation for writing these elements. So like this one, for example, would have a name like, would be the element associated to XX. If we call this one A, then this one here, for example, would be AXX. Um, so basically it was like XXX, YYY, ZZZ, and then here it goes XXX, YYY, ZZZ. And then because we took the divergence of the stress tensor, this is going to become in this form where it's actually now a vector. This is the x direction, this is the y direction, this is the z direction. And so if you were to do this with a computer, we already know all of these. We can just calculate these uh, derivatives and then put them into a matrix, put these into a matrix and just add them up, and we'll be left with this matrix that has some elements in it. And then we can plug each element into this, like we make a function for this matrix, or sorry, this vector, and plug it in. And so like for each direction, we would just have this term um, in our like within our equation. Um, for example, the momentum equation, the x equation, the pressure gradient d partial p partial x, then you would have this bunch of these terms, and then you would have all these terms. And so that's pretty easy with a computer. And also, again, as I mentioned last time, it turns out so this this mu um, viscosity term. As for bulk viscosity, I have no clue. Maybe there's an equation, maybe we don't know it. Um, Maybe it's a laboratory, maybe it's found in a laboratory to find out what that value is. Maybe it's assumed constant. I'm not sure. But obviously, in reality, these are not constants, and knowing them would be very important. And so this mu, at least we know, is determined by this equation. I believe this is empirically derived, something like that. But I think this equation is very accurate for our where we are, because you know mu doesn't really change very much dependent on temperature. The temperature range that we're looking at for the atmosphere, we're not going to these crazy drastic changes where T to the 1.5 becomes an actual issue. But basically it's determined by mu naught, which is this number, and also an initial temperature. And then you just plug whatever your temperature is into this equation and you'll get mu. So mu is actually a function of T. Um, you need to actually know the temperature to really know how friction is happening. Um, yeah, so I'm not exactly sure the way this works, but I think eventually if T gets big enough, you'll beat the T plus 200 term, and then mu will start increasing way faster. Um, and so now before I'm going to show how to calculate, like if we were to mathematically try to write out these tensors and try to get this divergence of the stress tensor. I'll show what that looks like. But first, I just want to show if we take this equation and we assume that the viscosity and bulk viscosity are constant, we can actually take things out and we'll get a really familiar term. This is the Laplacian, the the viscous force term that's usually used in the atmospheric equations or ocean equations, you know, and then there's this extra term with bulk viscosity, combination of bulk viscosity and viscosity. Um, and this will work in the case of compressible with constant mu and this. Um, but then if you assume the fluid is incompressible, like ocean water, for example, you can use the fact that it's incompressible, which means the divergence is zero. We plug that into this term, the whole thing goes to zero. So this whole term goes away. Then we're just left with the friction term. And in the atmospheric equations, this is actually the thing that I usually see being used. But I think more specifically, they actually try to parameterize this term, or they try to parameterize um, some of these terms here, which would basically mean like, you know, these equations, they change, they have an effect on such a small scale that they cause something called turbulence, which is basically, or, subgrid turbulence is one thing that does, because these turbulence things, they happen on such a small scale that our models nowadays, it will be comp like computationally very expensive to calculate them, and we don't even have the data on that level. And so that causes a lot of turbulence, which is these like kind of eddies, like very random eddies that occur in a fluid that cause it to kind of deform. And that's kind of what happens when you're in an airplane and it suddenly bumps, is like the air is doing something that's not really expected, and that really is coming from this. But it's also coming from, like, that's called turbulence. But subgrid turbulence, what I just mentioned, is if we were to run the full equations, or even run just this term, you would get these um, unresolved turbulence that will not exist in the model. And but we will not be able to understand turbulence in real life, because there are smaller factors, even at smaller scales, that are um, causing the turbulence to happen in real life, and then we end up getting a different solution. Um, and so turbulence is kind of a very important but hard to understand thing, and it actually turns out to be also pretty important for like convection, how clouds form. Because these terms can, we end up getting these different results when we try to model what happens to a cloud. And one of the reasons may be because the turbulence was not calculated correctly, or the parameterization was bad. Um, so we definitely do not want to use this equation for the atmospheric flow equations, but and we really, really want to use this one. This is what we would need to use. But it's so computationally expensive that currently the main focus is on parameterizing this, so we don't actually have to solve the whole thing. Because these are tensors, they are very, very expensive. You're pretty much doing a calculation for like 9 things for each thing, so it is very computationally expensive. Now, I'll just briefly go over how to solve for the tau tensor. So I took these things here, the gradients, the transpose gradient, the divergence times identity tensor, and you kind of just, add them together here. Um, you'll find, oh, du dx becomes 2 du dx. Um, all these terms add in the kind of way that we can't really collapse. And, on a diagonal, they're very similar. Um, And then so we make this subtraction. Now we get a term here. Basically, this term goes into here. All the diagonal terms get this extra term added to it. And now we have our tau. And we know that this is equal, we can just say this is equal to define it as tau xx, tau xy. So for example, this is tau xx, and this is tau zx, you know. So this is our tau, our stress tensor. And yeah, you can see there's a lot of shear terms, like how W increases in Y or something like that. Um, yeah, how W increases with X. So this X direction, this is the Z direction. It's saying, oh, like velocity, it's getting bigger and bigger, or it's going down. Um, that's shear. Um, so yeah, if you leave this out, you're leaving out a lot of things that are actually very important for like a formation of like clouds or low pressure systems and stuff like that. Hurricanes, all that. So, um, and I also want to first show for a second, like, how do we show that the divergence of the stress tensor, which is this like multiple dimension vector of vectors, how can we show that the divergence of that tensor, which we'll just call t, how can we show that that's a vector? So we'll just give this simple example for like a 2D tensor with elements a, b, c, d. So this would be txx, b would be txy. So the definition of divergence in a tensor format would be this. It would be the sum over j of dtij dxj. So you can pick I as x or I as y, and then for each time you loop through j. So you'd get um, d I is x, so here we have x is here, I is y, so you have y, and then it always goes x, y, and it's like this sum adds them together, so it's the x derivative of txx plus the y derivative of txy. Then this row will be the x derivative of tyx and the y derivative of tyy. And since we know that, A is this, B is this, C is this, and D is this, based on their location, we'll get this. And this is a vector with two elements in it. So yes. And if you were doing this in 3 dimension, you'd have a third element for the A hat direction. Um, yeah. So, so if we do that, we apply this, we take the derivative of tau xx and add up all these derivatives for these 3 rows. We will get that the divergence of the stress tensor is this term. So now that we know the term, we could go in with a computer, we could solve for this gradient, all of the gradients, and then we can add them together, for example, here. Then we take the gradient of that, then we add everything together, and we'll get this vector um, for each of our x momentum, y, and z equations, x, y, z. We could easily just solve these and add it on to our solution. Um, so that's nice. But again, it would be just as simple and maybe save a lot of time with coding or maybe avoid any mistakes to simply just code in some matrices like this, plug in these derivatives, add everything together into a single tensor, and then now you know the elements, then you know that the divergence is like this, and you'll simply get your vector in the same amount of time. Um, I, yeah, I think that is a much easier way than solving this out, but it is still interesting to see what each equation has. Like, um, we have things that look like they could be a Laplacian, But because these terms are not constants in this equation, and if they're constant, you get a Laplacian. But then you also have these other terms, like you would end up, let's say you say there's your constants, you would have 2/3 times mu, and then the x derivative of a divergence. Um, just very, very, very complicated physics going on here. Um, I've never seen anything like it, and I'd honestly be interesting to see what the effects of these are. Um, yeah, so thanks for the video, and sorry that in the past one of my old videos has an incorrect compressible friction force equation, but this is the um, actual one. And if you want to find this equation, you can go on Wikipedia for Navier-Stokes, Wikipedia, and they actually cite this textbook called Landau. Um, I have a copy of the second edition from 1987, so that is where I got it from. So if you get this one, it's page 45. It's equation 15.5, and they do not write it in this form. They write it in a vector notation. It's in the same form. Like it's just instead of using divergence, they use some sort of instead of using like gradient, for example, they use d dxi, and then divergence they'll use uh d dxl or something like that. But it's the same thing. And I think on the Wikipedia page, they write this one above the one that's in the Landau book. Um, I personally like this one because I get completely confused whenever I see vector notation. So um, yeah. So anyways, yep. Hope you enjoyed, and stay around for more videos in the future.